prove that Newton's first law is equal to momentum, Newton's second law is change in momentum over change in time, and Newton's third law is conservation of momentum. So, a lot to learn today. So, let us get started. Newton's first law is equal to momentum. Instead of writing momentum, we just can write P for momentum, right? Okay. All right. So, what is Newton's first law? Newton's first law is inertia at rest, right? And what is momentum? Momentum is inertia in motion. Let's dive into Newton's first law. Object at rest likes to stay at rest forever if and only if the net force is 0, right? Okay, if net force is 0, object at rest likes to stay at rest forever without any exception. What does momentum tell us? Momentum tells us the same thing. Object with same magnitude, object moving with same magnitude, V likes to keep same magnitude forever if and only if net force is 0. What does that mean? If object moves to 2 meters per second, we want to keep 2 meters per second forever, right? As long as the net force is 0, right? Okay. So, Newton's first law and momentum connected by the idea of net force is 0. Okay. Since we made that connection, we can give an equation. Okay, so that takes us to the equation. So, P for momentum. All right, so object momentum is equal to object times velocity, right? So, momentum is object, we can call it mass, times velocity, we can call V. So, momentum is mass times velocity, right? So, momentum is mass times velocity. So, what is the SI unit for mass? Kilogram. What is the SI unit for velocity? Meter per second, right? You have a scalar quantity, you have a vector quantity. When you multiply scalar quantity with the vector quantity, you get the vector quantity. So, momentum is a vector quantity, right? All right. So, let's do an example. I'm going to actually give you 2 examples, and you're going to tell me which one is an example of momentum and which one is not an example of momentum. So, I have a car, same car, right? Right, maybe mass 2, velocity. Which one is an example of momentum? Okay, this is not an example of momentum. Why? Because the net force is not 0. So, this is not an example of momentum. This is probably an example of Newton's second law or impulse, right? However, this is an example of momentum. Why? Because throughout net force is 0. Okay, and we can calculate the momentum. If I give you V is 2 meters per second, then this one has to be 2 meters per second, because this is same in magnitude, right? 2 meters per second, right? And if I give you the mass is 5 kilograms, so we can find the momentum. Momentum is mv. So, momentum is 5 kilogram 2 meters per second, right? So, momentum is 10 kilogram meter per second, and this is the SI unit for momentum, and this is the magnitude, right? And this is not a momentum problem. Why is that? Because this arrow is bigger than this arrow, right? If this arrow is bigger than this arrow, then there must have been some force acting between the location 1 and location 2, right? Okay, so this is not an example, and this is not also example of momentum, because there must have been some forces acting on it so that the car slowed down. This is also not an example of momentum. However, this is, because this arrow is equal to this arrow, the car is at the same magnitude from beginning to end. So, this is a momentum problem because the net force is 0, so acceleration is 0. Okay. So, Newton's second law is F equal ma, right? So, what did you learn from problem before? We learned that P is equal to mb, right? And we also learned A equal to delta V over delta T, right? Good. So we're going to use what we know. So F is equal to delta MB over delta T. So F is equal to delta MB is P delta T. So Newton's second law is delta P over delta T, right? This is another version of Newton's second law. Okay, good. So what is then change in momentum? Change in momentum coming from Newton's second law. Change in momentum is F delta T. And changing momentum has another name, impulse, right? Impulse. So this is impulse. Impulse is change in momentum. So this is impulse. All right. So the change in momentum is kilogram meter per second. And this is Newton's second, and they are the same thing. So that's impulse. This is the SI unit. SI unit for impulse is Newton's second or kilogram meter per second square. And kilogram meter per second square and Newton's second are the same thing. Newton's second is equal to kilogram meter per second. Why is that? Because Newton, maybe you want to make it red. So Newton is kilogram meter per second, right? Square, right? And you have another second over here. So right there, second. So second goes to second. So you have kilogram meter per second. Kilogram meter per second is equal to kilogram meter per second. All right. So they are the same thing. Mass is 5 kilogram, right? Velocity is 3 meter per second. Mass is still 5 kilogram. Velocity is now 7 meter per second, and velocity is this way. So what we want to find, whether it's a momentum problem or change in momentum problem. It's not a momentum problem because net force is not 0. How do we know? Because the velocity increases from 3 meter per second to, of course, 7 meter per second. So this is not a momentum problem. This is change in momentum problem. So let's find the initial momentum. What is initial momentum? Momentum initial is mv initial. So 5 times 3 is 15 kilogram meter per second. Momentum final is equal to mv final, and that is 5 times 7, so that is 35 kilogram meter per second. Number 3, change in momentum is equal to, of course, 35 minus 15, 20 kilogram meter per second, right? Okay, now we want to find the impulse. Number 4, impulse. Impulse is also 20 kilogram per second, kilogram meter per second. Why? Because change in momentum is equal to impulse. They are the same thing. Okay, number 5, if the force acting, right? So if the force acting on, like, let's say 0.2 second, what would be the force? Okay, so let's see, force would be delta P over delta T. So if it acting only 0.2 second, so 20 kilogram meter per second, and if it is acting on the object for 0.2 second, so this is 100 Newton, right? So F is equal to 100 Newton. Okay. So other thing I want to mention that the impulse can be same for 2 type of problem. All right. So let's consider this problem. Let's say Mr. Body jump from over here, from rooftop to concrete, and rooftop to where, what happened, the river. All right, this is 45 meter, right? Velocity would be same. So velocity would be he gonna be hitting the ground with 30 meter per second. Why? Because this is 3 times 10, 30 meter per second. In this case, is velocity also 30 meter per second, and Mr. Body is, is 100 kilogram. So what does that mean? That means the initial momentum is 0, right? Both case initial momentum is 0 because he was at rest on the rooftop. The final momentum would be, and this is also going to be momentum, 3000 kilogram meter per second, right? Both case he experienced same impulse, right? Same impulse, right? So what is the change in What is the change in momentum? This is the P final, this is the P final. So change in momentum is P final minus P initial. So this time is 3000 minus 0, and this time is also 3000 minus 0. So the change in momentum is 3000, all right, but force probably not going to be 3000. So let's find the force when he hit the concrete, all right. So let's find the force when he hit the concrete. So force is delta P over delta T. So delta P is 3000 and delta T is, let's say, since he falls on concrete, it takes almost no time. Let's say 0.001, right? 1 millisecond. So force would be, force is 3 million Newton in this case. Let's check this case. All right, so force is delta P over delta T. The change in momentum would be 3000, right? And this one gonna fall on the river, so it's gonna probably take a long time, let's say 10 seconds to come to stop completely. So this is 300 Newton, right? And this case you got 3 million Newton and 300 Newton is huge difference. When you fall on the concrete, your body come to rest at 1 millisecond. When you fall on the water, your body come to rest at 10 seconds, and that makes the huge difference. When change in momentum happens in a fraction of a second, there is a big force. Change in momentum happen within a fraction of a second over here. That's why you have a 3 million force. Change in momentum happens with a longer amount of time, so we have a smaller force. Okay, now we're going to do the last one. Newton's third law is actually conservation of momentum, right? And there is a great application of conservation of momentum in collision problem, like two billiard ball collide with each other, or a car collide with other car, or a star collide with other star, or moon collide with the earth. That happened, of course, before. So let's start with Newton's third law. FAB is equal to negative FBA. So we're gonna use momentum before. We're going to use two objects, a billiard ball A and billiard ball B. Billiard ball A moves toward billiard ball B, and billiard ball B moves toward billiard ball A. This is momentum before. What happened momentum after? After the collision, they change the direction. So now billiard ball A moving to this direction, billiard ball B moving to this direction, right? So now we're going to write momentum before is equal to momentum after, and momentum is always conserved, right? So we can write MA or MA VA plus MB VB is equal to MA VA plus MB VB. Now if we write that, there is a problem, right? We have to differentiate the after from before. Okay, so how can you do that? Maybe you want to use a symbol, maybe we want to use a prime to differentiate that equation from this equation. All right, so next few seconds I'm going to give you a proof of this one, right? Where this one coming from. All right, let's do a 3-column proof. Newton's second law. What is Newton's second law? You know, delta P over delta T, right? This is Newton's second law. So delta P is equal to F delta T, right? Okay, so what is delta P? What is the momentum on ball B? All right, so the momentum, change in momentum of ball B happened due to a net force, right? Due to a net force, all right, acting on some period of time, right? That's why change of momentum happened on ball B, right? So the change of momentum is, it can be written as momentum final minus momentum initial of ball B. So momentum final minus momentum initial, right? Momentum initial. So how can we write momentum final? Of course, you can put this one, and that's what momentum final means, is equal to F delta T. So this is the equation number 1. Now we're going to do the other one. So ball A. All right, so now start Newton's second law, delta P over delta T now, right? So delta P is equal to Ft. So far so good, right? Now delta P is equal to Ft. Now This is wrong. Why this is wrong? You are talking about the ball A, right? And ball A, look at that. Ball A moved to the west right now. So you have to be able to recognize that fact. The ball A now moving to the west. West means negative. So you have to put negative over here. So delta P is, of course, now you can put A over here, right? So now you can put M A V A minus M A V A is equal to minus F delta T, right? Again, you have to make sure that you put a prime over here, so to show that the momentum before is minus momentum after on ball A, right, due to a force acting on time, some amount of time. Okay, now we're gonna bring this one over here, maybe VA prime minus MAVA is equal to minus F delta T, right? So what do you know F delta T? F delta T is this one, right? F delta T is this one, right? This is F delta T. So I'm going to copy and paste this one over here if I can, right? I cannot, so I'm going to just write it down. So I'm going to just write it down what I see over here. M, maybe I have to change the color. So M VB prime minus MBB. What made a mistake I made? I have to put a parenthesis, otherwise there will be a problem here. Okay, so MAVA prime minus MAVA is equal to minus MB prime B plus MBB, right? Okay, so you're almost done. So you have mass A BA prime plus mass B BB prime is equal to mass A VA plus mass B VB, right? Okay, so we're almost done. So mass of ball A, mass velocity of ball A plus mass of ball B, velocity of ball B is equal to mass of ball A, velocity of ball A final plus mass of ball B times velocity of ball B final, right? So what do you want to call it? Now you probably see what direction we are heading to, right? This is called momentum before. What do you call it? This is called momentum after, right? Okay, and momentum is conserved, all right, throughout all type of collision. If it is elastic collision, momentum conserved. If it is inelastic collision, momentum conserved. That's what we're going to be talking about tomorrow. Different type of collision.